All right. Good afternoon, everybody. Thank you for allowing us to present the results that we got for this topic of inactivation of SARS-CoV-2 on servers in the built environment. And specifically, that word challenges will come up a couple of times in my presentation. I should recognize that I've not done this work all by myself. And one of my colleagues, Dr. Catherine Ratliff, is actually here with us. And she will be presenting work related to aerosol disinfection or the aerosol treatment studies later on the Friday morning. So don't leave early. That's what I wanted to tell you. So where do we start from? And this is kind of in a high level, and people already knows, of course, about the pandemic and everything else. So I'm not going to in a great deal there. But in the early onset, there was a great interest in how do we actually clean surfaces. Remember those days that everybody was wearing, going to the store and getting Clorox bleach and everything and wiping everything? Okay, so in those days, this is where this research started from. So at the same time, the US EPA, and I should point out, I'm in the Office of Research and Development, so I'm not going to talk about regulations here, just to let you know. There was a clear interest or a request came to us to find out, like, okay, how can we actually supplement any kind of ongoing treatment of surfaces, especially in areas or in locations where there's a lot of hand contact, like, guess what, we're in New York, in the New York subway system. So one of the technologies that was addressed was UV light, and that's where we actually came in and said, okay, we may have to take a look at if we can help out in helping our stakeholders, in this case, our mass transport agencies around the country, with information on how UVC would work for services in their specific environment. And it was always intended not to replace the standard treatment of services, your standard cleaning, but just to supplement it. And an example could be that you would do this at the end of the service of a line of a metro car, as illustrated in this picture. And when there are people not around, as a UV source, and then you would turn it around or take the lights out, and people would actually use that subway car again. So what was clearly to us was actually when we started looking at literature that, and I think we're still talking about it here, that applications of UVC in a more complex environment is not very well established. So how did we, the questions that we had were essentially the following, is like, how effective is UVC in inactivating SARS-CoV-2 on surfaces? Can we maybe use surrogate viruses, which makes life a little bit easier in doing more research for the same amount of money? And what are the parameters that impact efficacy? Clearly, the dose or the fluence clearly makes the major impact, and we have seen it already in many presentations. But also the material, and I think we have not talked about that here yet, so stay tuned. We also wanted to see what happens to the difference between dry and wet droplets, thinking about that if you are in a subway environment, the droplet may actually be on the surface and the UV does not get exposed at the same time, especially when you're talking about 254 nanometer UV lights. Far-UV would be a little bit different in that regard. And then we also wanted to think about what happens with the droplet composition. Are we talking about something that is in saliva or simulated saliva, or are we thinking about something that is more in the lab media, your tissue culture media? So the approach that we did was essentially a bench skill study in which we determined what the efficacy was for 3 different light sources against SARS-CoV-2 onto various surfaces. And the 3 sources were a Far-UV 222 nanometers, light source A, LED at 275 nanometers from a different vendor, as well as pulse xenon light. So the materials that we were interested in were far much more relevant to in transportation sector. And the ones that we selected on after consultation with our partners were ABS plastic, a stainless steel, and a bus seat fabric. And from own experience, knowing how the bus seat fabric looks like in this test, it's almost the same as what you're sitting on right now. So stay tuned for the results. So, and we want to address this in an applied setting. I point out there is a picture here of a test we did with Los Angeles Metro. Unfortunately, I'm unable to go into the details what came out of that, but that's made this research even more important. And I'll be happy to address it later on in the after this talk is over. So quickly, as it is in an academics, a lot of details about research itself. We use the SARS-CoV-2 isolate from 2020. I already alluded to, we use 2 types of media, either a tissue culture media in which the SARS-CoV-2 was added, or a simulated saliva derived from ASTM E2721 with a minor modification. Materials that are shown in this graph here are bus seat fabric, the ABS plastic, and the stainless steel. And the application of the virus in the various media was with 10 small droplets of 10 microliters. Does that mean that this is exactly how people would sneeze? Actually, no, probably not, but it still gives you some good idea of what happens, knowing that there are small and larger droplets onto a surface after somebody may have actually sneezed or coughed on it. And again, as I alluded to earlier, we were talked about looking at exposure to UV when the saliva in the media was still wet on the surface, or when it was actually already dried on the surface after a 1 hour delay time between the two. So the 3 light sources are shown here. It's a krypton chlorine filtered 222 nanometers source, a 275 LED, and a pulsed xenon. And the graph on the bottom right is actually a normalized to a spectral density, essentially, of the 3 light sources. So it's interesting to note how sharp or narrow those features are for 222 nanometers versus a 275 or a pulse xenon, which is a much broader wavelength than it is emission. I should point out that the 275 also included the 405 nanometers. The original design of that one was brought to our attention by the people who we worked with, and we unfortunately could not turn off the 405 nanometers, but we think that the efficacy data we got was predominantly based on the 275. So how did we do quickly the result, or how did we get the results? We worked with test and positive controls. They were extracted in conical tubes with standard procedures, 10 milliliters of cell culture media, and agitate for 50 minutes. And then we did actually use the TCID50 assays to quantify what was remaining. How did we obtain our dose response curves? We did it either with a light distance to the surface of 15 inches or 30 inches. That may already give you a hint of how difficult it was sometimes to inactivate the virus. And we did it for a contact time of 15 to 60 minutes exposure to the UV light. One thing I wanted to stress out here is that if you do this type of research, you should always pay attention to what is the natural decay of the virus. If you just start with a specific high virus at T equals 0 and you report your results based on the T equals 0 titer, you're misleading the public, because you are definitely going to see a decay of in this case, SARS-CoV-2 over a period of 60 or maybe 90 minutes. And if you don't take that into account, you give a great benefit to manufacturer of a UV source that is not warranted. So that's why this formula is there. Just don't use n equals 0. That is our opinion there. Last but not least, we also supplemented data to understand a little bit better with UV absorption measurements. And we tried to do that with the liquid sample itself. And we have some information about the dried media. And we also did a little bit of dimensioning of images of a droplet on a glass substrate. So here are some of the results. And I started actually, I will focus on the Far-UV because this is Far-UV conference. So what you see on this graph is 4 panels. And on the top left is a panel where you see essentially the dose response curve. Horizontal axis is the UV dose. And on the vertical axis is the log reduction. The top left is where you use tissue culture media and you have wet droplets on the surface. Again, you apply and immediately after that the UV starts. On the bottom, on the right, you see a simulated saliva, also with wet droplets. And then on the bottom, you have the same different type medias, but you have dry droplets that you were exposing the Far-UV to. And we also have the 3 different materials. So the black ones are the bus-seat fabric, the red dots are the ABS plastic, and the green as well as the blue squares are for the stainless steel. Stainless steel tests were repeated for the tissue, for the wet droplets, and that's why you see 2 data sets in there. So what are the things that you can learn from it? Well, first of all, if you think about materials like the stainless steel, if you wait long enough for the wet droplets, you will need to get to a point where you have a 4 to 5 log reduction in viable SARS-CoV-2, and you can completely inactivate the virus. I will never call it 100%. 100% doesn't exist for SARS-CoV-2. The other thing I wanted to point out is that if you look at the other materials, you see, for example, the bus seat fabric. that's the red, that is the black one. You don't see much of a difference there at all. I'm talking about half a log difference, and that's out for the wet droplets. And something similar happens on the simulated saliva side that is on the right here, and everything actually starts to drop down. So there is really a challenge there. And remember that simulated saliva is more realistic than tissue culture media. Now we're talking about dry droplets, and we don't see much at all. And we're not sure if we're the odd ones here in this project, so I'm happy to hear more about it. But we did not see any evidence that the Far-UV, at least at these doses, was able to get any kind of inactivation, very minimal, maybe down to 1 log reduction at best. Now, the point should be made that, of course, you can extend longer the period of time with the dry droplets, especially with Far-UV. You can wait longer, and therefore you may eventually get in some kind of efficacy that is helpful. But for a dry droplet, we did not see much of a good response. For the sake of time, I will just quickly go through what happens at 275 nanometers. And there we had the same problem as well. And now there's only 2 panels because now the red and the dry droplets are in the same graph. But again, we saw a significant change between whether you're looking at wet droplets or you're looking at dry droplets. However, for the wet droplets, actually, especially on the right side on the simulated saliva, we did see some reduction, some log reduction on the SARS-CoV-2. So it seems to be that the difference that we saw with the 222 and the 275 seems to be that the lack of efficacy for the dry droplets may actually in UV wavelength dependence issue. Have I told you that bus sheet fabric is doing anything? Yeah, it doesn't do anything, right? Okay, so why is that? It's a very non-smooth surface, and what we have seen clearly, and everybody probably knows that for many of these type of materials, the droplet actually sinks into the material itself, and your single light source is just not able to hit the virus where it is in between the fibers of it, and you don't get much of an efficacy at all. Very short, we saw similar. I won't go into all the details, but we have similar data for the pulse xenon, and the numbers are a little bit different. We still have to figure out how we can represent the data accordingly, because it's a broader distribution of wavelengths. So I normalized essentially to what intensity would be equivalent to 254 nanometers. So a little bit of supporting data that we try to do and figure out, okay, does that really help us in understanding? So UV absorption spectrum collected for the liquid itself. And we saw that there were indeed a significant difference between whether you're working with tissue culture media or with with the simulated saliva. So that's probably one of the reasons why we see the differences in log reduction between the 2 media. We also see that there's a difference between absorption for 222 nanometers and the 275 that I showed you, and the 254 kind of falls in the middle there. Last but not least is also that we have data for dry droplets. And in this case, for dry droplets, actually, we also see that there is a higher likelihood of absorption of UV light at that wavelength, although it is not as prevalent compared to the wet droplet. So that seems to be kind of not telling the whole story why we did not get any inactivation for a dry droplet. So the other thing that we looked at was, okay, what does an image look like? And people know about the coffee ring effect for various reasons. So we're not the first one to identify it, but clearly when you apply a droplet of, in this case, a simulated saliva droplet, when it dries, essentially it moves out to the edge and you get this nice coffee ring effect, and you can make images out of it, and you can essentially then demonstrate what happens there. Now, the trick is here, of course, that when you do then an absorption spectroscopy, you actually get a number for the whole surface. So that does not tell you what happens at the edges at the ring itself. So that begs the question, where the hell is the virus? Likely in the ring. So therefore, probably it may actually add up to a much more higher degree of absorption. And that may actually tell the story why you may not have inactivation of the virus at 222 nanometers. At least that's where we stand by right now. So in summary, we estimated some of the UV doses for the various light sources that I alluded to. Did see very minimal inactivation on dry droplets, and the absorption spectra do not tell the whole story there. For the light sources that we did see, it can be done at 99.9% or 3 log reduction, but you need to be much closer by, or you need more light sources nearby to get to the high dose. And that ties a little bit to the transportation sector, where they wanted to have a project that essentially would expose to the surface the UV light and have a quick turnaround time of only 50 minutes or half an hour to clean the subway car. And that just was not working based on what we found here. Last slide. I wanted to point out a couple of other things. If we were thinking about, and everybody's probably doing this, how we're going to put this into a built environment. There is a lot of challenges still with implementing it and the design. Using one source in one room is probably not going to work. You need multiple sources. I'm glad to see that the work that was done by Dr. Branders is definitely already considering that, and others are doing that as well. And even then, there's a likelihood that you will not always hit the surface at the right angle or the right place. Moving things around can work. Far-UV is not really intended for that, but if you think about a UV system, that would be the case. Last but not least, if you want to inactivate a virus on a fabric or a carpet, which is kind of more porous, it will remain a challenge. That's how we see, because it will hide in the crevices on canyons. And these three pictures that actually you show here is not even carpet. That's your stainless steel. That's I have to make sure that I say it right. It's a glass coupon and two types of stainless steel. And even there, it's likely that you will not always hit the viruses if you only use a single light source. And that's the end of my presentation. Happy to answer any questions if there's time remaining.
I have time for one question, so I'll go up here.
Thanks. John Yerger, Eden Park. I'm curious whether you tested the recommended solution that we would all have, which is to leave the light continuously on, and what the impact of that would be. Did you test that?
You mean an extended period?
No, all day. On all day while people are there. That's the way we recommend using it.
For Far-UV?
Yeah.
Yeah, okay. So no, unfortunately, we did not. No, but keep in mind that if you start with a wet droplet or something, you get in a self-inactivation, or so your SARS-CoV-2 load will go down, and probably after a day you may already have a 2-log or 3-log reduction. I don't know, the data is still out there how much it is. So
Yes.
Yeah, okay. Yeah, you're talking about a far much more applied setting. Yes, we did not do that. We stuck to a very short turnaround time. I understand that the Far-UV can be applied over a longer period. Yeah.
All right, thank you very much.